Okay, what I'm going to talk about here is a little bit about, this is not quite in the text, but I want to talk a little bit about fracture, failure. The next chapter, oops, you can't see it on right. There you go. In the next chapter, we're going to start talking about actually, what? No, in the previous chapter, we talked about this notion of designing axial elements and factors of safety and whatnot. And in those situations, we had a failure strain for a particular material, and given the failure strain and the factor of safety, we get an allowable stress. Allowable was the failure stress over the factor of safety, right? So the factor of safety basically knocks it down, gives you a margin for uncertainty, errors, overloads, unexpected things, and factor of safety, right? That's where it comes from. So let's talk a little bit about the failure stress. So if you look at a stress strain diagram for a typical engineering type of material, you have an elastic region, and usually you reach a yield, and then you start to get some amount of plasticity, and then at some point you get fracture. Sometimes this curve even this is the stress where it actually fractures. But you can see actually there's another peak stress. This might, some people might call it the ultimate. And also we have the yield stress. So which one would you consider to be failure? Well, the notion of failure depends upon the design, actually. So I talked about this in class probably, but so if you're designing door handle, yield would be a failure value or failure mode, in the sense that as soon as your door handle starts to yield, keep bending more and more, eventually it will not actuate the lock and unlock your door. So that design it has failed. Now, if you're talking about designing a I-pillar or a crumple zone in a car, in fact, it's not. It might be the fracture strength, because you want that element. You don't care that it plastically deforms. In fact, you want it to plastically deform, but you don't want it to break, right? You're not going to reuse that car once you run it into a wall, right? So, for that particular design, the fracture strength might be your criteria or the ultimate, okay? So it depends upon the design, right? Sometimes even just an elastic elongation is enough for a mechanism to bend, so it can be lower than yield, right? But those are typically the things we see, okay? So that's the notion of failure. It depends upon, we talk about yield, ultimate, and fracture. Now, we also have some other types of phenomena. Well, actually, before we get to that, so let's look at two materials. Actually, for those who have taken material science, appreciate this. Let's take one material. Okay, something like this. Okay, there's a lot of plasticity to it. Let's imagine that's a steel, and then you take the steel and you anneal it. So basically, yeah, increased stress where it yields. So here is material 1, and this is material 2. Think of it as two different steels. Two steels, one's been worked, and one hasn't. one. Think of it. All right, which one's better? Well, material 2, the yield for material 2 is higher than the yield for material 1. So if you're designing to that level, you might prefer material 2. And someone might even say, well, even the fracture is higher for material 2. The ultimate is higher for material 2 than material 1. So obviously material 1 is better. Well, that's not necessarily true. If you want to look at something like being able to absorb damage, you get quite a different situation. So a lot of times we talk about this notion of material toughness, or sometimes it's also called fracture toughness. Okay, this has to do with how the ability of materials to withstand plasticity, to withstand cracking, a little bit of immediate fracture. So if you look at the energy of the materials, first material can absorb that much energy before it fails. Right? This is the total strain energy failure for material 2. Now material 1 is quite a different situation. Right? Material 1, because it has this big plastic region, the amount of energy that material 1 can absorb until it fails is much greater than that for system 2. So it depends upon what your design is. So if you want to design something that wants to have a very high yield, and it never has any chance to put yield, and just a cable that acts in nice static loading, material system 2 might be the way. If you're designing a hull of a ship, let's say, where the loading changed a lot, where it's cracking, wants to see a lot of weird situations, and it doesn't look like fracture, or maybe some damage due to a weapon or something like that, material 1 is, okay? So, the toughness of the material, that's the amount of energy, the area of the curve, until it fractures. Sometimes also, when you take a material, you cycle it, cyclic loading. So let's say, platform, and this is done in such a manner that it vibrates up and down, so it continuously oscillates. Paper, right? So it's doing like this. There's some mechanism that makes it vibrate. What you find here is basically, as it starts to cycle, even though it might stay below yield, that over time, the stress at which it will fracture drops down. And that's what we call fatigue. Okay? So this has to do with cyclical loading. You have some situation like that if you're designing to. You don't want to use the stresses that you get from the static stress-strain curve in terms of failure stresses. You have to do, there's corrections for it you learn in design, Binder's rules, so on and so forth, plots, to help you see how much the failure stress has to knock down due to the way it's cycling. And that has to do with the amplitude of the cycling, the number of cycles, and also steady state cycling. Okay, that's fatigue. Also, sometimes in the opposite sense, we have parts that maybe are bars with a static load on it that's held for very long times, or where there's elevated temperatures, okay? Very high temperatures. What you see there is this phenomenon of creep. So over time, even though P is fixed, over time, the bar will actually slowly stretch, strain lengthens. In those situations, again, as in fatigue, the stress that you define as failure, and then therefore also the allowable stress, will drop because it's going to operate in a creep environment. There's other things that also knock down. Sometimes things like moisture, temperature, even things like being in a highly caustic environment, high amount of radiation, these can all affect the strengths of materials. And so when you're designing a component, you have to not only, you can't just blindly look at the stress-strain curves and failure stresses that are given in some tables, but you have to think about the environment in which it operates. Okay? So anyway, what are the failure stresses? This notion of fracture toughness, it's going to be the area of the strain energy is fracture. Fatigue phenomenon,